All right, our last conic section is called the hyperbola. Okay, you have seen this before when you graphed rational functions like 1 over x, and you got that graph that kind of curved towards these asymptotes in the first and third quadrants, right? The x and y axes played your asymptotes there. We will have graphs that have two asymptotes, in this case played by the diagonal lines. And you can see our graph is curving closer and closer to them on each side. So it's not like a parabola, it's a hyperbola. It's curving closer and closer to these asymptotes. And these are absolutely fun to graph. The way it's defined geometrically is it is the set of all points in a plane such that the difference of the distances from two given point is always constant. So what does that mean? It means if we take these focal points, or our foci here, and you were to measure the distance to a point, let's say a point here, and you were to subtract these two, find their difference, right? Meaning subtract. That difference, big one minus the small one, is the same everywhere. So if I picked a point here, and we measured the distance to my focus here, and we were to subtract them, that difference would be the same, the difference between the two lengths. So that's how it's defined for all of these points that exist. Okay. Now, here's how you draw them, and this is really fun. You start with your center, HK, and when it's horizontal here, meaning it opens left and right, in this case, we'll see in the equation x will come first. It's kind of the positive variable. Notice that unlike our ellipse, there is subtraction between them. In fact, if this was plus, this would be an ellipse. When it's minus, it's a hyperbola. So when you got one positive and one negative, hyperbola. Okay, if x comes first, if x is the positive one, is this horizontal case. And here's how we graph it. Whichever one is positive, we put this value a squared underneath. Doesn't matter which one, it could be x or y, whichever is positive. The second one, the negative one, we put b squared underneath, and we still have a relationship from before, the Pythagorean theorem. A squared plus b squared equals c squared. Okay, so check out these distances. So if it's horizontal, I go for my center, HK, a units left and right. So add and subtract a units, and we get to these points called the vertex, or vertices. Okay, so notice we add and subtract a horizontally to get to our vertex. Now when I need to get to the focus, we need to go c units left and right. So add and subtract c to get to these focal points. Okay, so there we go, add and subtract c. And might note, by the way, that if you did go up and down a and b and draw in a diagonal, kind of like Pythagorean theorem there, this distance, this diagonal, is the same distance as c. Anyways, nice relationship there. Okay, now to find the equation of these asymptotes, which you will not need to use to graph them, but to find their equations, it's y minus k, which by the way looks exactly the same right here, plus or minus b over a, so that's the slope of these lines. One's positive, one's negative, times x minus h, which again looks exactly the same right here. So some nice stuff to graph. Here is how you graph it though. We go left and right a units, we put some markers. That's where our vertices will be. We go up and down b units. We put some markers and we draw this rectangle. So you draw on a rectangle that goes through those 4 points, and through their diagonals, that's where our asymptotes will be. So it's a nice quick way of finding those asymptotes. Then I already know my vertices. We can just kind of curve my graph towards the asymptotes, knowing it opens up left and right. It's actually really fast and kind of fun to graph. Okay, so let's take a look really quickly. Okay, the vertical case is exactly what you would expect. Instead of x being the positive of the two variables, it's y. So we'd write that first. X is the negative one. And in this case, we will be going up and down to find our vertices and focus, and foci, I should say. So up and down A in the vertical direction, and up and down C in the vertical direction. And again, to find C, we'd use Pythagorean theorem. Now, a squared always goes with the positive variable for these. So whichever one comes first gets a squared, whichever one comes second is b squared. Okay, so you can see that the rectangle size I used on these two is exactly the same, We might be going sideways, we might be going up and down. It just depends on which variable is positive. Okay, the only difference with the asymptotes is that you do have the reciprocal slopes. So that's it. It's A over B rather than B over A to find them when it's the vertical case. Okay, let's identify the orientation, meaning do they open up, down, left, or right, coordinates of the center, the vertices, the foci, and equation of our asymptotes. Okay, for A, because X comes first, this is horizontal, where it opens left and right. Okay, for the center, we just need H and K as usual, which in this case is -2, +1. We're opposite signs here. For our vertices, we need to go left and right A units. So we're going to take our H value and add and subtract A. Okay, well, remember, A squared always goes underneath the +1. B squared goes underneath the second. So if A squared is 9, that means A is 3, and B will be 4. So in this case, we're adding and subtracting 3A. Now, because these are nice values, we can go ahead and actually calculate the location of both of these. -2 plus 3 is 1, 1. -2 minus 3 is -5, 1. So there are our two vertices. Okay, now if this was plus or minus, square root of 3 or some ugly radical, you could probably leave it as one expression here. But go ahead and calculate them out when we can. Okay, our next one, let's find where our foci are. Now we need to go up and down left and right C units. But we don't know C yet. And that's again where we go back to Pythagorean theorem, like we have before. A squared is 9, B squared is 16, and you might even recognize this as a 3, 4, 5, right? 3 squared, 4 squared, 5 squared. And in fact, C here is 5. So if we add and subtract 5, and again, because these are nice numbers, we'll go ahead and calculate the two individual points. -2 plus 5 is 3, 1. And our second one, -2 minus 5 is -7, 1. All right. Next, let's find the equation of our asymptotes. Okay, so it does y minus k, which by the way, it looks exactly like this, y minus 1, equals plus or minus, we'll just write them both together, b over a, 4 over 3, times x minus h, which is exactly what this looks like, x plus 2. And there we go, there are the equations of our two in point slope form. You don't need to calculate those out. Again, if you're graphing this from your center, you just go left and right 3, up and down 4, right? So 4 in the vertical direction, 3 in the horizontal direction to draw that rectangle, put your asymptotes through it, etc. Okay, here's the second one to try out. See if you can find all these points. If you don't get a nice value for C like 5 and it's a radical, that's fine. Just simplify it and maybe you can leave your answer as plus or minus that radical. You don't have to go to the kind of individual separate ones like we did here. Try B and then unpause the video when you're done. All right, should have come up with that this is vertical because y is first and our positive of the two. The center would be at 3, 0. Our vertices, we would need to go, in this case, up and down A because it's vertical. Remember, A here is 2. The bottom is A squared. So 0 plus and minus 2, we can individually calculate those two. To find our foci, we need C. So we need to go back to Pythagorean theorem, plug in our A squared and B squared, and calculate C, which ends up being the square root of 20, or 2 times the square root of 5. Now, normally we can leave this expression here, but since it's 0 plus and minus 2 root 5, we could simplify that to just plus and minus 2 root 5. And lastly, for our asymptotes, y minus 0, for y minus k is just y, and a over b, 2 over 4, reduces to 1/2. So we went ahead and reduced that here for our slope, and then wrote x minus h, x minus 3 right there. Okay. All right, let's move on. Here we are again. We need to complete the square to change these from general form to standard or center form. So this case, we kind of can look at this, and if one of our squared variables is positive and the other is negative, we can tell this is a hyperbola right away. So, and because x squared is positive, it's going to come first. And I already know this is also a horizontal hyperbola. But like before, let's pair up our terms with x. Okay, let's also pair up our terms with y. Negative 25y squared minus 50y. And let's go ahead and put that 116 on the other side by adding it over. Let's get rid of that constant. Okay, now for x, we need to complete the square. And because we're lucky, we got a 1 in front of x squared, we don't have to divide something out of both like we did for some other ones. We can go ahead and just do it plus blank. Half of negative 6 squared. Remember again, half of b, the middle term or linear term here, squared. So half of negative 6 is negative 3, and that value squared is 9. So we need to add 9 to both sides. Now y is going to be a little more complicated. We need to factor out negative 25 from both of these. Remember, if there's a coefficient in front of y squared, we got to divide it out of both. So when I divide that out of both, we're left with y squared plus 2y. And that's where we set up our blank. Okay, half of 2 is 1, and 1 squared is 1. So again, half of that value squared ends up being 1. Now keep in mind, we're not just adding 1 on this side. Again, remember it's negative 25 times 1, which ends up being negative 25. So for all of these values over here, we get 116 plus 9. Negative 25 times 1 is negative 25. We'll need to combine all those. And let's go ahead and write our perfect squares here. Half of b is negative 3, so x minus 3 squared. For our y values, we have this negative 25 on the outside. Half of 2 is 1, so y plus 1 squared. Equals, now I need to add all these up, which gives us exactly 100. Okay, now remember, for both ellipses and hyperbolas, we need this set equal to 1, so we divide everything by 100. That will turn this equal to 1. Here, there's nothing to simplify with the 100, so this just stays x minus 3 squared over 100. Minus 25 and 100 will reduce. Dividing each by 25, we'd get a 1 up top. And dividing by 25, we'd get a 4 in the bottom. And there is the standard form of our hyperbola. We can see, again, it's horizontal. X is positive, y is the negative 1, and we've got it in our nice center form. Okay, here's one for you to try out, completing the square. Again, we want to put the positive one first, which this case will be y. So you might want to write y on the left, just so we end up in this correct form at the end. Try this one out, and then unpause the video to see how you did. All right, we should have ended up here with y plus 1 squared over 4 minus x minus 2 squared over 49 equals 1. So you can check the work here. We added 163 over. We paired up our y's. We put y first because it was the positive of the two, which does mean this is a vertical hyperbola. It opens up and down. Factoring out 49 from both of these, you get y squared plus 2y. Half of that squared is 1. Make sure you add 49 times 1. Remember, it's really 49 times 1 on this side, so make sure you do the same there. Here, factoring out a negative 4 from both of these, you get x squared minus 4x. Half of that squared is 4. So add negative 4 times 4 again. Negative 4 times 4 is what we added to this side. Make sure you do the same here. Combining all these, we get 196, which is 14 squared, by the way. And then you can divide everything by 196. This and this should nicely reduce away, and we get nice denominators of 4 and 49. Okay, next it says write the equation of the hyperbola given in centered form. So we're going to write that centered form. And the first thing I notice about E is it's opening left and right. So I know we have kind of the generic form where x will be the positive value. And that would be over a squared. It's a hyperbola, so there's minus between them. That would be over b squared equals 1. Okay, so here's our generic form. And all we need to know is the center, hk, and the lengths of a squared and b squared. And we have our formula. So let's first go ahead and identify the center. The coordinates here for our center are right 1, down 1. So negative 1, 1. So there's our h and k. So let's go ahead and fill those in. That's going to be x minus 1 squared up top and y plus 1 squared up top equals 1. Now we just need to figure out a and b. So remember, if it's horizontal, a is the distance we'd go left and right to the edge of this rectangular box. So we can actually count that out. This is 1, 2, 3 units, right? 3 units to get to our vertex. So a has to be 3. A equals 3. And underneath we need to write a squared, which is 9. A squared is 9. Okay, to go up and down, b units to get to the other edge of this rectangle, and they did help us out by drawing it in there. So this is 1, 2, 3, 4 for b. b is 4, and underneath this we need to write b squared. So 4 squared is 16. And this is the equation of the hyperbola they gave us. That wasn't too bad. So again, remember, a is always towards our vertices from the center. B is always the other direction of our rectangular box here. Okay, see if you can figure out F on your own and then unpause the video to see how you did. All right, here you go. It should end up with y plus 2 squared over 9 minus x squared over 25 equals 1. Again, our center here was 0, negative 2. So remember, because it is vertical, we're going to use the formula with where y comes first. It's opening up and down. Since y is negative 2, y minus k, kind of looking like the opposite sign here, y plus 2 squared over a squared. So what is the distance to get to my vertice from the center? That's 3 units. That's a, and a squared would be 9. How far do we need to go to get to the edge of our rectangular box here? That is 5 units. So for b, or b is 5, or b squared is 25. And there you go. There's the equation of our hyperbola. Okay, we'll do some more examples. I know I didn't do very much. We're given an equation, just graph it. We'll definitely do examples like that in class. Just know this, drawing this rectangle in from our center and putting in our asymptotes makes these really, really quick to graph.